Hello everybody! Today we'll be going over post-contest analysis of Codeforces round 756, the last Division 3 round. We'll be going over problem D, weight assignment for tree edges. A short statement of this problem is, we're given a tree. A rooted tree. We are also given a permutation of the nodes. For instance, the permutation could be something like 0, 1, 3, 2. Our task is going to be to assign weights to these edges over here, such that when we sort all the nodes by their distance, we obtain this permutation. For instance, suppose if here I were to set weight 2, here I were to set weight 3, and here I were to set a weight of 5, this node is at a distance of 0, this node is at a distance of 2, this node is at a distance of 3, this node is at a distance of 2 plus 5, 7. So, if we sort our nodes, we should get 0, 1, 3, 2, which matches up the order over here. So here we found a valid solution. Obviously, there's some cases where it's going to be impossible. There's no solution. So, we must also say this in this case. So, over to the constraints. The constraint is that n is smaller or equals to 200,000. Okay. Great. So, are there, first of all, any ideas for how we could solve this problem? Yeah. Alright, I'll give a hint. So the hint is that we can think about a greedy approach. So first of all, we'll try to determine whether a solution exists or not. So an important fact to note is that suppose if I would have another permutation. For instance, if I have a permutation where I have 0, then some other nodes. For instance, I have 0 appears at one position, then I have, for example, 2, and then 1 and 3. This permutation will not be possible because the distance of node 2 will by definition always be bigger than the distance to node 1, which is pretty much obvious since all the weights are positive. So, we need to check for one case if the permutation is valid. Every time we're coming on a node, if we go through the permutation from left to right, we should make sure that its parent has already been visited. So in this case, what happens is that we go over node 0. 0 has no parent, so it's okay. Then we move to node 2. The parent of 2 is 1. 1 has not already been visited in the permutation, which means that there is no solution. This is not valid. So now we can easily deal with a case where no solution exists. Now, how to deal with a case where there is a solution, and how can we determine it? Because we need to determine the solution. So what we can do is pretty much easily make an observation that's going to be crucial over here. Since we said that the distance of a child will always be strictly greater than the distance to a parent, we can just greedily assign values for distances. So if I were to come up with another permutation that is valid, for instance, here a valid permutation would be 0, 3, 1, 2, because the parent of each node appears before it. Then what we could do is that let's just assign distances greedily. So this node should be at a distance of 0. This node should be at a distance of 1. This node should be at a distance of 2. And this node should be at a distance of 3. If this is satisfied, we have a solution. Okay. Now, if we make an observation, let's put them over here. How can we determine the weights of the edges? Well, simply to determine the weight of an edge from node x to node y, it's going to be the distance of y minus the distance of x. So here, 3 minus 2 is 1. 2 minus 0 is 2. And 1 minus 0 is 1. So now we have a solution to this problem. So recap. First of all, we can simply check whether each parent of a node is included in the permutation before it. And if yes, there's no solution. Otherwise, we prove that there is a way to generate a solution in any of these cases. Since by definition, if the parent of a node appears before it, the distance to this parent will be smaller, thus the weight of the edge is positive. Now let's look at a sample solution code. Okay, so what is happening in this code? First of all, we are inputting a tree as the parent of every node. So we're simply inputting, the parent of node I is this value. Then we just do minus minus to 0 index it because it's given in 1 index. Then we do the same thing, P. P will denote the permutation over here. So we put the permutation. Then added is going to be an array of booleans that is going to indicate whether or not we have already visited a node previously in the permutation. So we initialize it to false. Then what will happen is that we go through all our nodes in the permutation over here, from left to right, from I0 to I smaller than n. We look if the parent of this node has not been added. So if this node is not the root, because it means it has a parent of -1, and its parent has not already been added. Basically, not already been added means that its parent appears previously in the permutation. This is what it means. So if its parent has not been added, it means that its parent will appear somewhere later in the permutation, and we prove that this led to an impossibility. There's no solution. So in this case, we just output -1, which states there's no solution. Otherwise, we mark it as visited. So we say that yes, it has been added already in the permutation. And then I mentioned that we should set the distances, and we can just do this easily with 0, 1, 2, 3. So we just set the distance of pi to assigned distance, which is 0 originally, and we just do plus plus. So we just add 1. So we set it to assigned distance, and we add +1 to assigned distance. So all the distances are distinct. And finally, what we have to do is that we look for every edge, and we do distance from I. For example, over here, we look at distance to node 2, over here, which is 3, minus distance to the parent of this node, which is over here, 3 minus 2, and we get 1. And so, we just proved that this is going to be positive, because in the case where the parent appears afterwards, this should be negative, and obviously, in this case, it is impossible. And so we just output it. So this is an accepted solution which runs in 77 milliseconds, so pretty efficient. So here we covered the whole problem overall. So just to shortly come back on what was needed here, the most important thing was to think about a greedy approach to solving the problem, along with properly establishing all the relevant proofs over here. And on the implementation side, it was obviously not such a hard problem to code. So this brings us to the end of the analysis of problem D from last Codeforces Div 3 round. Feel free to like, subscribe, share, and comment. Thanks.